Okay, guys, it's just a quick run through. This is April 16th. I titled this Limits Which Require More Thought Than Rules. I'm hoping that at this point, a lot of you will look through here and go, man, that makes sense. I'm not really bothered by that. But some of these are a little tricky. And for a person just getting started with limits, which you guys are, sometimes they can be kind of bothersome. So you've got some rules when you approach when x approaches an actual value. You've got rules when x approaches infinity. Well, those rules are probably fairly comfortable for you, except when you start getting weirder things like this. So look at number 1, and let's just take a look. This says the limit of this graph as x approaches infinity. Now, a lot of you may look at that and go, I don't even know what that looks like. Now, I know what it looks like if you really think about it, but I'm going to show you how to do it without it. I know what an e to the negative x graph looks like. Remember, an e to the x starts flat along a horizontal and climbs up. Well, an e to the negative x starts high and comes back down. And that horizontal asymptote that it follows is the shift. So this graph right here is really just, as you move to the right, it's approaching 3. Because it's approaching the asymptote y equals 3 right there. So I know that my limit's 3, but let me give you an idea what to do in case you don't think about the graph. So hypothetically, if I were able to plug that infinity in there, I would get this, right? And again, e to the negative infinity. What would an e to the x graph do as I went towards, how would I graph an e to the negative infinity graph? Well, normally an e to the x graph goes like this, right? So if I had a regular e to the x and was heading left, it would flatten out at 0. 0 times 52 is 0, then add a 3. But it might be easier when you get those negative exponents just to do this. Put the e to the negative infinity in the denominator as e to the positive infinity. Now you have a massively, rapidly growing number in the denominator. The top is staying constant, and it doesn't matter how big that is. It could be equal to 1, it could be equal to 1 billion. This is eventually going to dwarf that in size, and when the denominator grows more fast or more rapidly than the numerator, just like when it has a higher power, all of that approaches 0 when you approach infinity. So if that's a 0 and that's a 3, when you evaluate those limits, the sum of them is just 3. All right, what about this one? If I plug an infinity in there and infinity in there, I'm getting the natural log of infinity and e to the infinity. Well, if you think about the natural log graph, it looks something like that. So as I move forever to the right, this is approaching infinity on the top. The e to the x graph, however, also approaches infinity as you move to the right. You can see it going up. So the actual fraction, who knows what that graph looks like, but I do know that this particular one is growing fastest. It's a faster infinity, faster growing one, because exponential is going to outgrow any of the other power functions, natural log functions, anything else other than perhaps another power function. So because this is growing faster in the denominator, I know that this is approaching a 0. Okay, now this one's a little tricky too. A lot of people look at this and they think, oh, well, if I were to plug an infinity in there, as sine goes forever to the right, it's oscillating between -1 and 1. And then they say, oh, well, then the limit doesn't exist. They write D and E and they miss this problem. So even though it is true that as you move to the right, the sine curve is oscillating between -1 and 1, it actually does have some value as you continue to move to the right. Maybe it's -1, maybe it's -0.5, maybe it's +1/2, maybe it's 0. Regardless of what it is, this value, as I put an infinity in there, is going to be something between -1 and 1. Now, if that was all there was to the problem, I would say, well, a number between -1 and 1 is not a y value, so I would say D and E. But the fact that I have this on the bottom tells me the bottom is growing to infinity, right? So if the top number is stuck between -1 and 1, it remains pretty small, right? And the bottom number is growing with leaps and bounds, and if the denominator is growing so much faster than the numerator is, then I would have to say that the fraction is approaching 0. All right? Over here, I look at this and quickly I can determine exponential functions, even if the power in the even if the power in the powered function, the exponent is really high, like 10 or 100 or 1,000, doesn't matter. Eventually, as you move to infinity, this is going to be approaching infinity much faster than this one. And if it does, if the faster or larger infinity is outgrowing the smaller infinity, I would have to say that the actual fraction is approaching infinity, but I do have to check the sign. Would it be positive or negative? Well, as I go to the right here, I'm going up and to the right. And then remember powered functions, if the lead number is positive, then it's up to the right. So plus over plus, it must be a plus infinity. So, dang, you missed all of that. Here, one more time. As I move to infinity there, 2 to the infinity, we know that that's exponential function. So as you move to the right, it's going positive infinity. And then x to the 10th, remember, polynomials, if you have if you have a positive number in the front, you're going up to the right. That's also positive, so plus over plus is plus. Had this been like a negative 3 or something on the bottom, that would be plus over minus, and I would say negative infinity. But the bottom line is because the top is growing faster than the bottom, I got to say that it's going to infinity there. Sorry, barking dog. That will be a perennial problem throughout this spring. Okay, so number 5, we've got the h function is a piecewise function composed of this rational function at 4, and it's equal to 8. I'm sorry. A rational function everywhere but 4. And again, this right here, that is the same thing as writing this twice and saying, hey, one of them is less than 4, one of them is greater than 4. It's just a shortcut way of saying, hey, this function's going to look like this everywhere but at 4. And then at 4, it looks like that. So it says, and this is a very common style of AP question. It says, which of the following statements are true about the function h? The first thing says the limit of h exists as x approaches 4. So I need to check the limit from the left and the right. Well, this not equal 4 means left and right. So I'm going to plug 4 in there, and I get 16 minus 16 over 4 minus 4, so I get 0 over 0. And we know when we get 0 over 0, what does that mean? There's a hole, and holes have limits. So I know that the limit exists right now. If you want, you can factor it and actually find it. But this problem doesn't really ask you to find it. But look, I could. And then I could plug the 4 back in and get the limit of 8. But this limit definitely exists. Then it says the value of h of 4 exists. And h of 4 right there is also equal to 8. And then the last thing says h is continuous. Now, at this point, I actually need to go in there and make sure I found that limit. So if I hadn't already, to answer this question, I would have needed to here. Because remember, a function is continuous. And you know this part's continuous because it's a rational function with just one break at 4. And this is a line, y equals 8. So the only place it could possibly not come together is at 4. So when you check at 4 to check continuity, the limit existed, yes. The value existed, yes. And they were both equal to 8. So it is continuous. So this would have to be 1, 2, and 3. All of them. All right. I'm going to zoom back out a little bit since I keep missing... you keep missing what I'm doing. All right, look at number 6. This was kind of a tricky problem from an old AP test. It said the table of the function values for f are in this table. It says the table illustrates that. So here you got a table, bunch of x values starting at 1.1, ending at 1.0001, and the y values are starting at 0.9 and ending at 0.9999. So what is this saying? Okay, so as I'm reading this, it looks to me like what's going on with x? 1.1, 1.01, 1.001, 1.0001. As I move along, what does it look like the x is getting closer to? It looks like x is getting closer to 1. Now, you got to be careful because all of them have x going to 1. But is it coming in towards 1 from the right or from the left? Well, I see it coming in from the right because this is bigger than that. So as this comes in from the right, I got to go, well, I must be approaching 1 from the right-hand side. Well, that alone right there is enough to eliminate everything else, but let's go a little bit further, okay? And then this one, the y values, what are they doing? 0.9, 0.99, 0.999, 0.99999. It's getting closer and closer to a y value of 1. Well, that confirms it. Now, some people look at this and go, yeah, but what about this? I could be approaching 1.1. Well, if If I was approaching 1.1, it looks to me like if I read it this way, it looks like I'd be approaching 1.1 from the left side. So it can't be that. So really the only way to read this would be that it's approaching a value of 1 from the right-hand side, right? Because you'd be like 1.1, 1.01, 1.001, 1.0001. You're getting closer and closer from the right-hand side, and the Y value is approaching a value of 1. So anyway, that's a way that AP has asked that question about limits in the past, making sure you understand it. All right, so it says, if you were to graph the following function, what would the graph look like as you approach an x value of 5? Now remember, as I approach an x value of 5, that's essentially saying what's the limit of this function as x approaches 5. Now, the limit of that function, if I plug a 5 in there, gives me 10 minus 10 over 25 minus 50 plus 25, and I get 0 over 0. So most people look at that and say, oh, it looks like a hole. But if I take this and I factor a 2 out, and I take the denominator and I factor it into x minus 5 squared, or x minus 5x minus 5, that cancels. And look what happens when I redo the limit now. I get 2 over 0. What does 2 over 0 mean? Oh, vertical asymptote, right? So it ended up not being a hole at all. So don't jump to conclusions there, and always think. That's why every time I ask that question, I say, when you get 0 over 0 when evaluating a limit, what does it typically mean? Yeah, typically a hole. But make sure you can't cancel out what appeared to be a hole. In this case, there actually isn't a hole at all. The only thing that's happening at x equal 5 is a VA. All right? All right, number 8 says find the value of the constant that will make this continuous. Well, what is this? Well, this is a sine graph, and sine graphs are continuous. This is a line, it's continuous. And when you put them together, the only place that possibly that could be undefined or have a hole in it would be at 0. So at x equals 0, you'll notice it doesn't even exist there. So everywhere else I should be fine. There should be no undefined values. So that part is great, except possibly at 0. Now this is, if k is a constant, then this is just a linear function. Negative x plus whatever 2 and 3k end up adding to give me. So this function only exists at 0. So it really is just a point. At 0, you get whatever you get there. Well, to be continuous, what would this have to do with this? This would have to basically fill in the hole that has. Because think about it, if I plug a 0 in there, I get 0 over 0. That's a hole, right? So I don't, this function right here kind of gets, if you actually graphed it, it kind of does this along the x-axis, and then it jumps up to 4, has a hole, and then comes back down and wiggles. But I don't know that. So I just got to make sure this is true. So let's think about what we know about continuity. According to continuity, the limit has to exist, which means the limit from the left and the right. That's this, left and right, less than 0 and greater than 0. If I plug a 0 over 0, I get in there, I get 0 and 0 when I evaluate that. But wait, I've got a trig rule. Any trig of something x over something x is 4. So the limit from the left and the right side is 4. So that's the limit. Now the value is what happens at 0. If I plug a 0 in there, I get 3k plus 2. Well, these have to be equal in order for it to be continuous. So there you go. All I got to do is solve. I subtract a 2 and I get 2. I divide by 3 and I get k would have to be 2/3 in order for this to be continuous. Because if it's any other value, then this hole doesn't get filled in by that point. All right, number 9. Number 9, you've seen these square root functions, and the temptation again, is to just look at that and go, oh, a square root of x squared is just a single x, maybe some other junk with it. But the problem with that is, remember, a square root doesn't give me x when I square root an x squared. It gives me the absolute value of x. And we know that absolute value has a right arm and a left arm when it's linear. And the right arm is the positive x. It's just whatever you have in there. But the left arm is the negative x, right? Well, I'm going left. So for me to simplify this, I have to basically, I'm going to come down here. For me to simplify that absolute value and to get rid of it, I've got to keep the top part. And then I'm going to take the absolute value of that and change that to a negative x. Now, everything else would have changed signs too, but at this point, does it matter? Limits to infinity when the powers match, use your coefficients. Ends up giving me 4. And we've seen that before. This one, much easier. Cube root of 125x cubed is 5x something. over 12x. And why don't I need absolute value? You can put the 7 in there. Why don't I need absolute value? Because it is an odd powered function. It doesn't have absolute value. And then look at this. Any limit to infinity, whether left or right, if the powers match, 5/12. So I didn't have to change any sign here because of the odd power, even though both of those were going to infinity. Now, if it's going to positive infinity, like number 11, the square root of that 16x squared is what? Absolute value of 4x something. The bottom is still 2x plus 5. And when I reevaluate this limit, I don't need to change the sign, because if I'm going to infinity, I'm going to the right of that, not to the left, right? And if I'm going to the right, I keep the sign. So this just becomes a regular old 4x plus something. And then once again, like powers, 4 over 2 is 2. So I hope you're getting the hang of those. 12, people look at 12 and they just struggle all day. They plug a 0 in there and they get 1 minus 1 is 0 over 0. And they go, what do I do? Some people try to break it up. They try to do this. I hope somebody in here is like, no, wait a minute. You told us about this. And I did. If you try this, you end up getting dne minus dne, because this is 1 over 0, and this also is 1 over 0. Now, I know it's tempting to go, hey, d minus e minus dne minus dne is 0. It's tempting to say that, but it actually is not a true statement. You did get this problem correctly, but that is not true. You could, a dne minus dne could very well be 0. It could also very well be 4 or dne. Or negative infinity. So do not do this. Right now, this is just a rule on your sheet. If you go back to those little trig tricks at the bottom, I have this and I said, for now, you're just gonna have to memorize it. So you need to just memorize that's equal to not that, but 0, all right? And also it's true if I have cosine x minus 1, if I flip that, that's the same thing as just factoring a negative 1 out. But that's gonna give me 0, and when you learn L'Hopital's rule, it won't bother you at all, because you can take the derivative of that and get 0 really quickly. Okay, right here, don't make the mistake of saying 8/4. Remember, you always plug a 0 in first. When I plug a 0 in, I get 8 over tangent of 0, which is 0. What does that mean? It means there's a VA. Is the bottom squared? No. So if you're going towards 0 from the left and the right, you're going in different directions, must be dne. We've talked about those before. All right, sorry. Again, 8 over 0, when you plug the 0 in, that means VA, and because the bottom is not squared or absolute valued, I know it can't go in the same directions, and if it's going in different directions, it must be in dne. And then 14, if I plug a 3 in, I get 9 minus 18, which is negative 9, but I get a 0 on the bottom. What does that mean? It means there's a VA, right? So that's not my answer. What does it mean? Well, vertical asymptotes, when the bottom is squared or absolute value or something that ensures no matter what I plug on the left and right side of 3, like 2.9 or 3.1, it's going to be positive. And no matter what I plug in here, like 2.99 or 3.01, it's going to still be really close to negative 9, and a negative over positive would go to negative infinity, because again, I know I have a VA. So it turns out if you want to plug in 2.99 there and there and there, and 3.01 there and there and there, you can, but you'll probably never get done with the test taking that much time to figure that out. All right, negative infinity. All right, jumping over to the back side. Okay, number 15. If I plug a 0 in there, you're going to go, wait a minute, where do I plug it in? Exactly. If there's no variable, remember pi is not a variable. It's 3.1415926 or whatever that is. I know you guys have it memorized to like a zillion places, some of you. But there's nothing to plug in, so that means that this is a constant. So all you have to do is simplify it. So tangent of pi over 3, we know that's the tall reference angles. That's a root 3. Just carry over the 2, and you're done. Finished, okay? Number 16, plug a 0 in. Sine of 4 times 0 is sine of 0, that's 0. 3 times 0 is 0, and sine of 2 times 0 is sine of 0, that's 0. So I'm getting 0 over 0. What does that mean? There's a hole. It's not an answer. So I'm going to put this over this and that over that. And when I put sine of 4x over 2x, it's one of my rules. And again, it gives me 0 over 0, guys. That's why I can use the rule. So 4/2. And then when I put this over 0, this over that, again, when I do the limit, I get 0 over 0. So I can use the rule, 3/2, but I'm subtracting. And when I subtract those, I get 1/2. But remember, you can't apply that little A over B deal until you know that the problem is 0 over 0. All right, so here, I can't deal with cotangent, so I'm going to swing it down. Although 2 is a constant, it's fine to stay there. It is not inside the parentheses. They are inside the trig function. So I'm going to bring this down as a tangent. And this is a little bit of a tricky problem. When I plug the 0 in there, I get 2 on the top and 0 times 0 on the bottom. So what does that mean? VA. Now, a lot of people right there say, oh, there's a vertical asymptote. So, and the bottom's not squared. So it must be going to, it must be DNE. But wait, even though it's not squared, these are both tangent graphs. And if you were to look at these tangent graphs, and we've seen something like this before, a tangent of 3x just has a smaller period than a tangent of x. I'm not being exact here. But think about it. As I look at this vertical asymptote, as I approach it from the right side of 0, what's happening as I approach 0 from the right side of each of these? Well, they're positive values. So both of these end up being positive values as you come in from the right. Well, what happens when you come in from the left side? Both of those are negative values. Well, if I come in from the right, I got a plus plus. That's infinity. You know that it's infinity or negative infinity, but 2 pluses right there give me a positive over 2 pluses. I know that's going up. Coming in from the left side, I have 2 negatives down there. Well, 2 negatives is also a plus. And I still have plus over plus. So this must actually be going to infinity. Now, that's a really tough problem as far as limits go. A lot of people write DNE. And if you were to write DNE on your test, there's a good chance I'll give you credit. Sometimes I actually give bonus, but because these will probably be multiple choice, there's a good chance that I'll just take both. All right, 18. I have this crazy limit. This honestly goes above and beyond what I'm going to give you on your test here. I believe, well, I'll tell you what, let's just give it a shot. So I'm trying to go to infinity there, and I'm like, what the heck? This is not like anything I've ever seen. But what would happen if I square rooted that x squared? I get absolute value of something. And then I get this minus x right here. Okay? And then if I'm heading towards infinity, I'm doing the right side of this, which means that just becomes a regular x right here. So when I look at this problem, it's really tempting to go, oh, the x's cancel, must be equal to 0. The problem is there's something going on from this, and I don't know what it is. Okay? So this is a problem I'm not going to give you on your test, but let me just show you what you can do. What I can do, and if you remember multiplying by a conjugate, I'm going to zoom in on this so you can really see it. Okay? So what I can do is actually, I'm going to rewrite this original problem down. What would happen if I forced the limits hand by multiplying by the conjugate of the numerator on the top and the bottom? Now check this out. This is a practice a lot of people use when they're evaluating limits. But since I don't have face-to-face, I'm probably not going to get this dirty here. All right, so here we go. I'm multiplying by the conjugate, all right? And I'm going to go ahead and multiply this out. Now, these are binomials, right? That minus that plus that. And because it goes like a minus b, a plus b, I can FOIL it, but the OILs are going to cancel. So I'm going to go first times first, which gives me just a regular x squared minus 12x. And then the outside and the inside are going to cancel, and then I'm going to go last times last, and I get that. And then on the bottom, all I have is this. All right? And then don't forget, you're still trying to evaluate this limit. Okay? Now, at this point, my x squareds cancel. And what ends up happening is now I have a fraction, and I've got rules for infinity with fractions. So let's take a look at this. I've got this negative 12x on the top, and on the bottom, I've got this absolute value problem. Well, what if I took the I have this square root problem. What if I took the square root of the x squared? Now look what happens when you write it as an absolute value. All right, and then if I'm going to the right, what happens? I'm going to use the right part of the absolute value, which is positive x something. And then now look what happened. Because now you have a fraction, this part, this dot, dot, dot part doesn't matter. Check it out. Right now, let me move this over so you can see it. Right now, this dot, dot, dot part doesn't end up mattering because you get this negative 12x over this 2x plus dot, dot, dot. Whereas before, the dot, dot, dot would have mattered. But now it doesn't because all you're looking at is the highest powers. And negative 12 over 2 is negative 6. So that is a really tricky problem. That has been on an AP test once. And I want to say something like 78% of the people missed it when there were 5 multiple choice answers. So a baboon or a cat or a mouse would have gotten it 20% of the time. And on this one, something like, it might have even been 88% missed it. Whatever it was, it ended up being a really brutal problem and it defeated the laws of probability. But I throw it on there every now and then just to show you a little clever manipulation. You can bank on not seeing this problem, number 18, on your test. All right, number 19. Number 19 is probably the most viewed limit in the history of limits. And when you plug a 0 in there, you get natural log of 1, which is 0, minus sine of 0, which is 0, over 1 minus cosine of 0, which is 1, and 1 minus 1 squared is also 0. So I get this. And the question is, well, what in the heck do I do with this limit? This is uglier than I've ever seen. And I got to be honest with you, there are some strategies you can employ. Like, we know that 1 minus cosine squared is sine squared. That might get us somewhere. But I threw this on here just for fun. If you have ever seen the movie Mean Girls, okay, the movie Mean Girls, that's the limit that got thrown up on the screen that Katie Heron or whatever her name was got right to win the Mathlete Championship. So anyway, little comic relief there. But that, if you remember, she was like, oh, and she remembered something stupid about Aaron's hair being so pretty that day and whatever. If you haven't seen Mean Girls, it's worth the view. It's I know you're probably watching the crud out of movies. Go watch that. But that limit shows up, and actually the limit does not exist. I don't know of a great way to evaluate that other than to maybe graph it. And if you graph it, it actually does not exist on either side of that 0. I mean, at 0. All right, this is one we've actually seen before. It says the limit as x approaches negative 4 from the right. So I know that if I plug a negative 4 in there, I get 0 over 0. So I know that I'm thinking there's a hole. But actually, this graph does not have a hole. There's actually a jump here. It definitely does not exist at negative 4. But to check negative 4 from the right side, all you got to do is pick something to the right of negative 4, like negative 3.9. And if I plug negative 3.9 in there, what's negative 3.9 plus 4 in the absolute value? Positive 0.1. And what's negative 3.9 plus 4 there? Also 0.1. And that gives me a value of 1. Okay, because I get 0.1 over 0.1. Another way to do it is say, wait, if I'm going from the right side, I'm going to use the right arm of this, and the right arm of this doesn't change the sign. This cancels and leaves me 1, and the limit of 1 is 1. All right, so a couple different ways to think about that. If you ever want to know what the graphs of these look like, the graph of this, you're going to go over to negative 4. And at negative 4, there's a hole at positive 1 and negative 1. And it does that to the right, and it does that to the left. So it's y equals 1 to the right, y equals negative 1 to the left. And if you keep plugging values in for x, whether it's 5 and 5 or 6 and 6 or negative 10 and negative 10, negative 20, negative 20, you see that you either get positive 1 or negative 1, but nothing right there. All right, 21. It's a piecewise function. What do we say? I mean, a step function. What do we say about step functions? They jump at integers. All right, so at every integer, it's hopping up to the next step. So if this had just said x approaches 5, I would go, oh, at 5, it's hopping to a new step. Limit doesn't exist. But this says 5 from the left. Well, as long as it's not at an integer, just plug the number in. And again, I can't plug 5 in, but 5 to the left side would be like 4.9. Because remember, at 5, it doesn't exist. It's jumping. It's where it jumps to the next step. So I'm going to plug a 4.9 in there. And what does the greatest integer function do to a 4.9? It rounds it down to 4. All right? And then the next one, this says the limit at 2. Well, the limit at 2, that's a no-brainer. It's a step there. So if I'm jumping at 2 and I'm not checking right or left, I know that that is not going to exist. And then finally, I have a limit of a greatest integer function at 2.7. Well, 2.7 is not an integer. It's in between 2 and 3. So in between 2 and 3, you just have a flat step. And where is that flat step? Well, plug it in and see. plug in a 2.7, and it rounds down to 2. All right? All right, so the last couple questions. This one, you're probably really familiar with these, but notice I don't ask you a lot of questions except domain and where is it continuous. So for domain, you've got to check a couple things as well as continuous. So let's get started. First of all, this literally is the domain of each of these functions. So right here, I can say, wait, I'm going forever to the left from -2. This exists between -2 and 4. This exists between 4 and 5, but includes the 4. This only exists at 5. This exists between 5 and 7, and that exists bigger than 10. But one thing I snuck in here was that this right here, even though this rational function exists there, there's a vertical asymptote at 3, and 3 is in that interval. So even though I can graph this between -2 and 4 on a graph, it has a VA there. And domain, I can't plug that 3 in. So when I come through here, I'm going to say, all right, the domain is everything less than a -2. And look, it's not equal to -2. So I could write it two ways. I could say that, or everything between -2 and 4, but wait, 3 doesn't exist. So I could say everything between -2 and 3, or, and I don't like this notation, I'm going to use interval notation. So interval notation says from -infinity to -2 parentheses. Union, all right, and then this would be -2 to 3, union, and then the next one would be from 3 to 4, so 3 less than x less than, but let's be careful, 3 all the way to, do I stop at 4 on domain? No, because it's equal to 4 there. Do I stop at 5 on domain? No, it's equal to 5 there. Do I stop at 7? Well, I have to. Even though it's equal, I have to stop because this doesn't pick up at 7. It picks up at 10. So I got to go from 3 all the way to 7, and then I can put a bracket around it. Now, I said earlier, guys, sorry. I said earlier that we'd never put a bracket around a number when you're dealing with continuity like we are in 25. But this is domain, which you are rarely asked about on limit sections. But their domain means 7 is included here. I can plug a 7 in. I do get an answer. And then after 7, again, don't pick it up at 7. Don't pick it up until 10. So at 10, everything greater than that all the way to infinity. So I could write here 3 less than x less than 7 or equal to 7. And then or x is bigger than 10. So I could write it like that or I could write it like this. This is by far the best way to write it that I know of. And now let's check out continuity. All right. I'm going to shrink this down so we can go back because this is important right here. This is going to be much trickier for continuity. All right. So let's check this out. So for continuity, not only does the graph have to exist, and I just wrote down where it existed, but the limit has to exist at those breakpoints. Okay. So let's look at all these breakpoints. Right now, I know I'm going to begin at -infinity because this right here is a parabola that goes forever to the left. It's just going up to the left and up to the right. But this one really goes up to the left because it goes forever to the left of -2. Now, at -2, is it continuous? And I got to say no, because if you look back at domain, it didn't even exist at -2. There's no equal sign. So I'm definitely going to have to break it at -2. And you can put a comma or a union. I'm going to put a comma because of space. All right, then what happens next? Do I jump to 4? No, because remember, there's a VA at 3. And VAs are never continuous. So I'm going to split it at 3, all the while never using brackets. All right, now what about at 4? At 4, let's check the limit. Now I know it exists, right? 28 minus 8 is 20, but I haven't checked whether these two connect. Remember, if it's continuous, it has to meet those 3 rules. The value has to exist, and it does. The limit has to exist, and then they have to match. So let's check the limit from the left. If I plug a 4 in there, I get 20 over 1, which is 20. Plug a 4 in there, I get 28 minus 8, which is 20. It's actually equal 4 there, which is also 20. So the limit exists, the value exists, and they're equal. It must be continuous. So I am not breaking it at 4. So move on over to 5. Let's check out 5. You got to check the same thing with 5. Does the limit from the left exist? All right. 35 minus 8 is 27. Does the limit from the right exist? 25 plus 2 is 27. So the limit existed, and the value existed. It's 25. But the limit and the values two results were not the same. So because they're not equal, it's not continuous at 5, I've got to break it at 5. And then beyond that, there's nothing to worry about between 5 and 7, and it definitely stops at 7. So I'm going to go from 5 to 7, but I'm not going to put a bracket there. Because if I put a bracket there, what am I literally saying? I am saying that 7 is a part of this set, which means it would be continuous. But it's not continuous. Look, there's not even anything on the other side of 7. There's this big gap between 7 and 10. So even though that might have a limit from the left, and it might be equal there, it might have a value there, it doesn't have a limit for the right. So the limit doesn't exist. So I got to put a parenthesis there showing that 7 did not meet my criteria. And then I don't have anything until 10. Certainly, since there's nothing on the left side of 10, I got to pick up at 10. But I should be able to go to infinity on that line for the rest of the way. All right, so these are kind of tricky. All right, and you're going to have to probably enter one of those manually in your on your test. Okay, so looking at 26, it says, we mentioned this maybe briefly. It says, put the letter of the graph in the blank below if it has one of the following discontinuities. So there's 3 kinds of discontinuities we've talked about. Removable or point discontinuities. AP likes to use the word removable, but they use that as well. Point discontinuity means it has a hole in the graph. Well, which of these graphs would even have a hole? These have jumps because they're greatest integer functions. This is a polynomial. It's a cube function. It just kind of does that. And this right here is just a rational function with a VA. So the only one that possibly could have a hole is this one. And you can see it when I factor at x minus 2 over x minus 2. So at x equals 2, there's a hole. If it's got a hole, that would definitely be the removable discontinuity there. So A. And then a jump discontinuity. Well, we know about greatest integer functions, right? Even though this thing is shifted down to, these graphs at every integer just hop up to a new spot. Well, those are called jumps. So jump discontinuity would be right here. It takes care of that one and that one. And then infinite, those are vertical asymptotes. Well, this one is a polynomial. It didn't even have an asymptote or anything discontinuous. But this right here has a vertical asymptote at x equals 2, and you know that. So this would be the infinite discontinuity. All right? So hopefully that makes a lot of sense to you, and you would be able to go back through that again if you need to. But that is all I have for you on the 16th of April. And good luck. I've got one more review tomorrow for you guys, and then we're going to test on Monday. All right? All right, you take care. Miss you guys.